Hello and welcome to Network Theory. The module 2 is on time domain analysis of RLC circuits. Today we are going to be discussing about source-free and driven RLRC circuits. The references are Ravi Singh, William Haight, and Charles Alexander Anseliku, Fundamentals of Electric Circuits. We are going to be discussing the response of source-free. Source-free means there is no source in the circuit. Source-free RL and RC circuits, and also the response of driven. That means there is a source in the circuit. RL and RC circuits and some numericals. Now, speaking about source-free circuits and driven circuit, what are these? Now, a source-free circuit is when the source is suddenly disconnected. So, which means that, and we are speaking about circuits which contain inductors and capacitors. So, in such circuits, how does it function? Without a source, it can function if it has got some components like the energy storage components like the inductors and capacitors. Like for example, an RL circuit or an RC circuit which does not have a source is called as a source-free circuit. So here these are source-free, but how do they work? Or will there be any current in the circuit? There will be a current due to the initial stored energy of the inductor or the initial stored energy in the capacitor. So because of this, the circuit will work for some time till the energy is used. So that is what you mean by a source-free circuit. Now, the energy stored in the energy storage elements will be transferred to the circuit and causes the current to flow, like we said. Now, when there is a source, so a circuit driven by independent source is called as a driven circuit. So a driven circuit will obviously have a source in it, right? So this is the difference between source-free circuits and driven circuit, and these are very important when we're speaking about especially the source-free circuits. We can see that they can work whenever there are energy storage elements. Now, speaking about the source-free RL circuit, a source-free RL circuit looks like this. There is a resistance, there is an inductor, and there is no source. So we can say for the circuit to function, there should be some initial energy stored in the inductor, due to which there will be some initial current. Now this initial current, so if I write the KVL for this, you get an IR plus LdI by dt is equal to 0. And this is a first order differential equation. So this one is a first order differential equation what we are speaking about. And the solution of this is given by I is equal to I0 e raised to minus R by L into T. Now so I0 is your initial current. So due to the energy stored in the inductor has some initial current, and that is I0. So what happens is that since there is no source in the circuit, the inductor is going to be supplying its energy to the resistor and dissipate that energy in the resistor, and hence the current through the circuit is going to be given by I0 e raised to minus R by L into T. Here the time constant we define as tau is equal to L by R. Now, so obviously you can see that as time t tends to infinity, this becomes equal to 0. Current becomes equal to 0, which means that initially when it starts out, the current is I0, and after some time, whatever energy is stored in the inductor gets used up, and the current finally becomes 0. So if you observe the characteristic of the source-free RL circuit, it is something like this. Starting from current I0, it goes up to 0. So the initial current is I0. At time t is equal to 0, the inductor has some stored, because of the stored energy in the inductor, initial current is I0. It starts from there. Slowly the current starts decreasing. There's no source. Obviously the current will start decreasing and finally become equal to 0. We can see, and obviously that is understood by our expression, which is I is equal to I0 e raised to minus R by L into T. So at t is equal to 0, your current is equal to I0, and at t is equal to infinity, your current is going to be equal to 0 from the equation. Now if I put t is equal to L by R, then I is equal to I0 e raised to minus R by L into L by R, which is e raised to minus 1, or it is equal to 0.368 I0. E raised to minus 1 is 0.368. So we can see from the graph that at this, so this is called as, this L by R is called as the time constant, which is defined by tau. So at t is equal to tau, or t is equal to L by R. So when the time becomes equal to tau, or at L by R in this case, the corresponding value of current is what? 36.8% of your initial current, right? So or the current has dropped up to 36.8% of your initial current, and this is how the time constant is defined as. So the response of the RL circuit is an exponential decay, and this response is basically, what we can say is that is due to the initial energy stored in the stored in the inductor and the physical characteristics of the circuit, and not due to some external voltage or current source. So what you understand by this is basically that because of the energy stored in the inductor, there is current. So what do you mean by the response? We are speaking about the current in the circuit. So the current is due to the initial energy stored, and also the physical characteristics of the circuit, that means the values of the resistance and the inductance, but not due to some external voltage or current source. So that is why we call it as the natural response of the circuit. So this response, which is an RL circuit without any source, is called as a natural response of the circuit. Now let us try to understand some examples. Now here in this problem, here initially we had seen in an earlier video, we had seen spoken about initial conditions. Now initial conditions are what is stored initially due to the initial stored energy in the inductor. There will be some current in the circuit. Now you can see that at t is equal to 0 plus, you are asked to find out the values of current I, di by dt, d squared I by dt squared and all. So first let us observe this. At time t is equal to 0, the switch is being closed. So this switch at time t is equal to 0, the switch is going to be put into position number 2. So before time t is equal to 0, so before t is equal to 0, the circuit was in position 1, switch is in position 1, right? And we assume that steady state has reached in the circuit. So now let us, so for doing such problems, what we do is always draw the circuit for before t is equal to 0 or in position number 1. So drawing the circuit, 20 volt, and this is position number when the switch was in this position. See, when the switch was in this position, so one is connected to the 10 ohm resistance and the 1 Henry inductor. So the 10 ohm resistance and 1 Henry inductor are connected up in this case, right? And this is your 20 volt. So we are saying that at before time t is equal to 0, the switch was in position number 1 and it has reached steady state. Now, what is the meaning of that? That you have kept the switch for a long time so that steady state conditions has occurred in this in the circuit, which means under steady state, normally we replace the inductor. We have seen that the inductor by a short circuit. So under steady state, so after some time, the current through the inductor becomes constant as L is equal to, sorry, as V is equal to L di by dt. Current has become constant. Whatever current it has become constant. Then V becomes 0, or it is just like a short circuit because V is equal to 0 when I is constant, right? So this we have already seen. So we are just going to be replacing L by short circuit. So what will you have here? This is a 20 volt and a 10 ohm resistance, and the inductor is a short circuit. Now, what is the current? 20 divided by 10. So I0, we call this as I0 minus, is equal to 2 ampere because it is 20 divided by 20 volt divided by 10 ohm, and that is a current flowing through the inductor here. Inductor has now become a short circuit, but there will be a current, and this current is equal to 2 ampere. Now, we know that I0 minus is equal to I0 plus. What does this mean? When the switch at time t is equal to 0, now the switch is put to position number 2. So just at the instant that you put it to position number 2, that is just after closing the switch, changing the position of the switch, that time is called as 0 plus, and that current is called as I0 plus. So we know that through an inductor, instantaneous change of current is not possible. So initially, whatever current was flowing, which is denoted by I0 minus, the same current which will flow through the inductor just immediately after closing the switch also. This is what we have studied. Okay. So now we are going to be seeing. So the first case, what we found out was that I0 minus the initial current through the inductor is I0 minus, or that is equal to I0 plus, which is 2 ampere. Now here the position number 2, the switch is closed to position number 2 at time t is equal to 0. Now I'm going to be, so after t is equal to 0, so for t greater than 0, our circuit is going to be like this, that is 20 ohm, the 10 ohm and the 1 Henry inductor. Now what do you observe in the circuit? There is a total resistance of 20 plus 10, 30 ohm, and there is this 1 Henry. So this is an RL circuit, or you can call it as a source-free RL circuit. So this is a source-free RL circuit. Obviously, there is no source in the circuit. So I can write the current for the inductor, the current through the inductor as is equal to I0, we have already studied, minus R by L into T. What is I0? It is 2 e raised to minus of R by L. Now what is the value of R? R is equal to 20 plus 10, 30, right? So 30 divided by L, which is 1 Henry. So 2 e raised to minus of 30 into T. So this is my expression for the current through the circuit. You can see that obviously as time passes, or as time t tends to infinity, this current would be equal to 0. So after some time, the current would become equal to 0. Now we are asked the value of currents, different values you have asked. So you have been asked to calculate I di by dt and d squared I by dt squared at t is equal to 0 plus. Now we know I0 plus we have already found out. I0 plus we have already found out, that is 2 ampere, right? Obviously, even if you, so 0 plus is just time is equal to 0, just the instant after closing. So time is equal to 0 only. So putting time t is equal to 0, you can see that again we are getting current is equal to 2 only. So I0 plus is 2 ampere. Now, let us find out di by dt. Since we have I here, so I can find out di by dt. What will be di by dt? Di by dt will be equal to 2 into minus 30 e raised to minus 30t, which is minus 60 e raised to minus 30t. So, at time 0 plus, what are we going to find out? So, di by dt is equal to minus 60, because time t is equal to 0. Substitute time t is equal to 0 in this equation and you get minus 60. So this is a di by dt. So the expression would be minus 60 ampere per second. Similarly, if I find d squared I by dt squared, you can again di by dt, you have this equation. So d squared I by dt squared will be equal to minus 60 into minus 30 e raised to minus 30t, right? And this will give you 1800 ampere per second squared at time t is equal to 0 plus. So this minus 60 into minus 30 is 1800, and if you put t is equal to 0 in this, you get in this expression, if you put t is equal to 0, you get 1800 ampere per second squared. This is d squared I by dt squared. This is one way of doing it. You can also find out, that is, you can write the expression. So this is your inductor. You can write the differential equation, that is R into I plus L into di by dt is equal to 0. And from that, find out the value of di by dt, or d squared I by dt squared. That is also possible. So here, that is another way of doing it. But since we already know, we know the expression for a source-free circuit. So we can directly use this expression here and find out I di by dt, d squared I by dt squared, and so on. Okay. Now speaking about the source-free RC circuit. Now source-free RC circuit is this one. there is a resistance and a capacitance without any source. So obviously, like in the case of the inductor, the capacitance should have stored some energy, and then that energy it can supply to the resistor to make a current flow in the circuit, right? So you can write the expression for the voltage across a capacitor, and what we see is that the voltage across a capacitor is very similar to the expression. So initially we are assuming that the capacitor has got an initial voltage of V0 across it. So we are assuming that the capacitance has charged up to initial voltage of V0, right? So if there was a V0 across the capacitance, so initial voltage is V0 suppose, then your total voltage in the circuit is given by V0 e raised to minus T by RC. Here, RC is called as a time constant. So again, in the same way, like we spoke about for the inductor, in the inductor, we are speaking about the current, which is equal to I0 e raised to minus T by tau. Here, tau is equal to RC, and the time constant tau is given by RC. And you can again see that when T is equal to tau, or when initially when T is equal to 0, V is equal to V0, like we said before for the RL circuit. T is equal to infinity, voltage becomes 0, and at T is equal to RC, your V becomes equal to V0 e raised to. So if I substitute T is equal to RC, then this becomes e raised to minus 1. So V becomes equal to V0 e raised to minus 1. And e raised to minus 1 is 0.368. So this is equal to 0.368 of V0. A very similar diagram or a graph like in the case of the inductor current is drawn over here. So at time t is equal to 0, the voltage is V0. Then it slowly decreases exponentially and reaches 0. And at the time t is equal to tau, and we see that t is time is equal to RC. So at tau is equal to RC, the voltage becomes 36.8% of the initial voltage. So this is how the time constant in a source-free RC circuit has been defined. Now let us see an example with this. The question is that the switch is changed from position 1 to 2. So again, very similar to circuit, to whatever we did with RL circuit. Here the switch is changed to position number 2 at time t is equal to 0. Steady state having been reached before switching. Okay, so which means that before time t is equal to 0, it was in position 1 and kept for a long time so that steady state had reached. Again, you have to find out I di by dt and d squared I by dt squared at t is equal to 0 plus. So this is what is told. Now, again, let us do the same procedure. So in position 1, that is before t is equal to 0, right? So the time before time t is equal to 0, it was in position 1. So we are going to be redrawing the circuit or drawing the circuit like this. So this is 30 volt and you have a 20 ohm resistance because 30 volt, the switch is in position number 1 and this would be 30 volt would be connected to 20 ohm and 1 microfarad. So 20 ohm and we have a 1 microfarad capacitor. This is the 20 ohm. Now, again, we have to find out, we are assuming that what is written, steady state is reached before switching. So before the switch has been changed, this has been kept for a sufficiently long time that steady state has reached. So what does this mean? Which means that the capacitor can be, so once the capacitor reaches steady state, it would have charged to the full voltage. So what would be its voltage initial, whatever steady state voltage? It is nothing but V0, we call it as V0 minus, and that is nothing but, since the capacitance is connected across 30 volt, we can immediately say it charges up to 30 volt. Or in other words, capacitance in the steady state can be replaced by an open circuit. But when does it become an open circuit? When it is charged to the maximum voltage, whichever is your supply voltage here in this case, right? So the capacitance will be, since it's connected across a 30 volt, V0 minus is 30 volt over here. And obviously, this is the same as V0 plus. So which means since an instantaneous change of voltage is not possible for a capacitor, Whatever voltage was there across the capacitance before time t is equal to 0, just before time t is equal to 0. Now, immediate when the switch is closed at time t is equal to 0, it is going to position number 2, but the capacitance voltage cannot immediately change, so V0 plus is going to be equal to 30 volt only, right? Now, you're asked to find out, so now what is the circuit now after time t is equal to 0, so at t is equal to, or for t greater than, let me see, for t greater than 0, our circuit looks like this: 10 ohm, 20 ohm, and you have this capacitance. Now, what is the capacitance charged up to? The initial voltage was 30 volt, right? So the capacitance had a voltage of 30 volt across it, and there is a 30 ohm resistance through here. So what would be the current? It would be 30 volt divided by 30, which is the current value will be equal to, or you can also write it. This is now, in other words, we can say this is a RC circuit, which is source free. There is no source in the circuit. Now, what is the voltage of the capacitance? It is going to be equal to V is equal to V0 e raised to minus T by RC. This is the expression. What is V0? It is 30 volt, and e raised to minus T by RC. So V0 plus is nothing but, if I put T is equal to 0, I get V0 plus is this one. This is one. Now, if I am asked the current, now current is nothing but that is equal to I is equal to V by R. So it is, the current value is going to be 30 e raised to minus T by RC, which is the expression for the voltage, because the current is going to be starting from here divided by the resistance. Total resistance is 30 ohm, because our circuit is 10 ohm, 20 ohm, and the capacitance, right? So this is our circuit, capacitance of 1 microfarad. Now, so which means that your total resistance in this case is 30 ohm. So V divided by R, you will get this one. And the current is going to be equal to e raised to. So we can write the value of the current as equal to e raised to minus T by RC. So at time t is equal to 0, I is equal to 1, right? So your current is going to be 1 in this case. This is the expression for the current at time t is equal to 0 plus. I hope you have understood. You can also understand like this. There is the capacitance is just like acting like a voltage source. Voltage source connected to resistance of 30 ohm. What would be the current? It will be 30 divided by 30, which is 1 ampere. So current would be 1 ampere at time 0 plus. Now, what is a so obviously you can find out now, if I you have 1 ampere, then you can find out di by dt. So this is the expression for I. You can find out di by dt, d squared I by dt squared, etc. like in the normal case. Again, put time t is equal to, so if you are asked to find out di by dt at time t is equal to 0 plus, find out, differentiate this, put t is equal to 0, and you will get the expression for di by dt. And again, the second differential, or again differentiate di by dt, you get d squared I by dt squared. Whatever value it is, put time t is equal to 0, you get d squared I by dt squared at time t is equal to 0 plus. So this is how you can do such problems. In the last problem, we were asked to find out current I, di by dt, etc. at 0 plus. Now here we are asked to find out the voltage at 2 millisecond. This is a circuit with a capacitance, and you can see that at a time t is equal to 0, the switch changes to this position, which means that yours 2 microfarad and 800 ohm can get connected together as a source free circuit. So initially, before time t is equal to 0, what is the condition? Initially, this switch was in this position when there is a source in the circuit, right? So there was a source, and what happens? Your circuit has been kept for a long time so that the circuit has reached steady state. So now let's try to draw, like always. What do we do? Always draw the circuit for before t is equal to 0, or we are finding out for 0 minus right? So I'm just going to be drawing this. This is our circuit, which is 50 volt, 2 microfarad, and this is 732 ohm. So this was a circuit before time t is equal to 0, and it is if it is not set, normally the system is kept on for a long time so that it has reached steady state. Now, once it reaches, so you can see that the 2 microfarad capacitance is connected to 50 volt. Obviously, after some time, it will charge up to 50 volts. So its initial voltage will be nothing but V0 minus would be equal to 50 volt, and you already know V0 minus is V0 plus, so that is equal to 50 volt. Now, so find V0, we have found out V0. Now, V of 2 millisecond, what does that mean? You are asked to find out the voltage after at 2 milliseconds. That is, obviously this is after time t is equal to 0. Now at time t is equal to 0, what is happening? At time t is equal to 0, or for t greater than 0, your circuit, the switch has changed to position, this position. So if I call this as position number 1 and this is position number 2, now the switch has changed to position number 2 here. And redrawing that circuit, so we have an 80 ohm here, 800 ohm here, 800 ohm, and there is a 2 microfarad capacitance. Now we can obviously see that this is a source free circuit, and if it is a source free circuit, then what would be the voltage across it? The voltage is given by V is equal to V0. We are asked to find out the voltage V across the capacitance, right? This is what we are supposed to find out. So the voltage across the capacitance is given by V0 e raised to minus t by RC, where what is the value of R? We have to consider this. This is your source free circuit. R is 800 ohm, right? And V0, we have already seen it is 50. So what would be your value? It would be equal to 50 e raised to minus t by RC. R is 2 and 800, 2 into 800, 10 into 10 raised to minus 6, 2 t by RC. This is our value. Substitute the value of resistance, capacitance, and time is equal to 2 milliseconds. So this is the general expression. This one is the general expression. So for finding out the voltage at 2 millisecond, you put t is equal to, in this problem, t is equal to 2 milliseconds. Substitute that and find out the value of voltage, right? So if I substitute, I get it is equal to 50 into e raised to minus of 2 into 10 raised to minus 3 divided by RC. Our resistance is 800 into 2, which is 1600 into 10 raised to minus 6. And you solve this and find out the value of V. This is how you can solve for such problems. Okay. So now we have seen source free RL and RC circuits. Now let's see what is driven circuit. So driven RL circuit, you can see a typical. So this is a very, very simple, very straightforward case of a voltage source, and there is a series switch which is connecting resistance and inductance together. So R and L are connected to the switch, and at time t is equal to 0, the switch is closed, right? So what do you understand here? The current before time t is equal to 0, the switch was open, because of which the current through the inductor would be 0. Obviously, it is open, and if it is kept for a long time, the current would be 0 through the inductance. So once you close the switch, the inductive current would start from 0, and slowly it would start increasing. So it's an exponential rise, and it would slowly increase towards its final state. Now, what would be the final state? How can you find out the steady state? You assume that the inductor is a short circuit. So once you replace the inductor by short circuit and the switch is closed, so if I make the switch closed, your switch is closed and you have this RL circuit. So this is how the circuit is. And what will happen? So if I replace the inductor by short circuit, so this is now, this is now V0, suppose that is your input voltage, and R and L, then the inductive current the steady state inductor current can be found out by replacing the inductor by short circuit. So if I replace inductor by short circuit, the current would be V0 by R. So the final current would be V0 by R. So what is going to happen is, as the switch is closed, initially the inductor current was 0. Slowly it will start rising towards a steady state value of V0 divided by R. Right, and this is an exponential curve, which has the formula, or the expression will be V0 by R into 1 minus e raised to minus R by L into t. So the expression V0 by, so in this expression I can see it as V0 by R. If I split it, it is V0 by R e raised to minus R by L into t. Now, if you observe this, it has got one part which is called as a steady state. So whenever we have driven circuits, or the total response, you can say that it is composed of two parts. This is a steady state part, steady state response. You can understand steady state response means what? Final value, or final value which the circuit is going to have. So at time t is equal to infinity. So if you see, observe this expression. At time t is equal to infinity, this part becomes 0 and you are left with V0 by R. So at time t is equal to infinity, the final current through the inductor is going to be equal to V0 by R. This is called as a steady state value, and this is called as a transient value. So any such circuits will have the total response will be the sum of the steady state response plus the transient response. And you can see, like we said before, the transient response is called as a natural response and it will die out after some time, whereas a steady state response is the constant one and it will remain. So for here, if I put in this expression, if I put t is equal to L by R, which is the time constant, we get an expression here. So I is equal to V0 by R into 1 minus e raised to minus 1. That is, at time t is equal to tau, or L by R. If I put t is equal to L by R in this particular expression, this becomes V0 by R into e raised to minus 1. So 1 minus e raised to minus 1, the value e raised to minus 1 is 0.368. We have already seen. 1 minus of that comes out to be around 0.6. So effectively, I can say that it is around 0.632 of V0 by R. So in such cases, the current starts from zero and increases, and the time taken by the circuit to reach 63% of its final value is called as a time constant. So the value time constant remains same, tau is equal to L by R only, but the way it is defined is now different. In the source free circuit, the current was decaying. The time taken by the current to decay to 36.8%. Now here the current is increasing. The time taken by the current to reach to its 63% of the final value is defined as a time constant. This is for a typical, very simple driven RL circuit. Having said that, this if the circuit is of this nature, then you have a nature of current like this. But there may be we'll see cases like that. It may not be so simple also. So do not use the formula just like this, V0 by R, because after switching there may be some other voltage source, there may be other resistances, etc. in the circuit. So this is just a general awareness of how a driven circuit is going to be. This is for a driven RL circuit. Now we have the case of a driven RC circuit. So similar to the RL circuit, we have the RC circuit here. As the switch is closed, the capacitance is going to be charging up to the voltage Vs. So you have a source voltage. Before time t is equal to 0, switch is off. So obviously after some time, the capacitance voltage would be 0. And when you immediately close the switch at time t is equal to 0 plus, the capacitance voltage would be 0 only, and slowly as the switch is closed, after some time the capacitance starts charging up to the voltage Vs. So you can see under steady state conditions, the final voltage across the capacitance will be equal to Vs only, right? So the capacitance, the nature of the voltage would be something like this. The capacitance would charge up from 0 and slowly rise up to the final voltage of Vs, right? So, and your expression can be written in this form: Vs into 1 minus e raised to minus t by Rc. So the same thing at t is equal to Rc, which is the time constant. We are at time t is equal to RC, which is nothing but tau, your V becomes equal to is 0.632 of Vs. So what is the final voltage? It is Vs, and the time taken by the circuit to reach 63% of the final voltage is called as your time constant. Right. So this is the nature of the voltage across a for a driven RC circuit. Okay. Now we are going to be speaking about the total response. Total response, like for example, when we have a circuit where there is a switch and you have some components like the inductance and resistance, like an RL circuit or RC circuit, and then there is a switching happening. What happens is that, and the switches, so, and if there is a source also, so obviously there is some source in the circuit, and switching is happening. So the response is nothing but the voltage across the capacitance or the current through the inductor and so on, right? So we can say that the total response can be said, or the complete response can be said as a sum of the natural response plus the forced response. So in other words, the natural response, we already called it as the transient response, and the forced response is the driven response due to the source. So due to the source, you have a forced response, and due to the natural elements, due to the physical nature of your components, you have the natural or the transient response, right? So in general, we can write that f of t can be written as a, which is the steady state value, plus b e raised to minus t by tau. So let me say f of t is equal to, this is a very handy expression which we are going to be using when we have switching in the circuits. Now f of t is equal to a plus b e raised to minus t by tau. A is a constant, so a is called as the steady state response, and this part is going to be your transient response. So like I said, the total response. So what is f of t? Now f of t can be either the current or the voltage. It is a response, right? So either the current through an inductor or the voltage across a capacitor and so on. So depending upon whatever is the case, we can use this. Now we see that if I put t is equal to infinity, at time t is equal to infinity, f of infinity would be equal to, if I put t is equal to infinity, this part becomes equal to 0. So I am ending up with a. F of infinity is a. And if I find out f of 0, putting t is equal to 0 here, I'll get a plus b. So f of 0 will be equal to a plus b, which means that the next point what we can write, f of infinity is a, and f0 is a plus b. So b can be found out as equal to f0 minus a, or f0 minus of f of infinity. So from this, substituting, I can write f of t, the general total response, can be written as a. A, what is a? Substitute for a as f of infinity. Substitute for b as f0 minus f of infinity. And we get this expression that is equal to f of infinity plus f0 minus f of infinity e raised to minus t by tau. Now, this expression shows that you have a steady state f of infinity. Infinity is corresponding to the final steady state response. And this is a constant d, which is corresponding to f0 minus of f infinity. So why is this very important or handy is because in circuits where there is switching, and there is after switching, if there is a source in the circuit, we need to find out, for solving the circuit, we need to find out the steady state value, that is at time t is equal to infinity, at time t is equal to 0. So f of infinity and f0, if you find out, and if you know the time constant of the circuit, you can find out the total response of the circuit. Now let's see how this is done. Okay. So here we have a problem where the switch is closed at time t is equal to 0, and we are saying that the steady state having previously been attained, and find I of t for t greater than 0. This is what has been asked. Now, switch is closed at time t is equal to 0. Now, observe here. So, at time t is equal to 0, the switch is being closed. So, which means that the switch was opened before that. And if it is open, then this is just an open circuit. And you have got a 10 volt and 20 volt in series. with the 30 ohm, 20 ohm and the half Henry, right? So let's redraw the circuit for finding out t is equal to, so we want to find out I'm using the expression used before. So for that I need to find out, we are asked to find out the current through the inductor. This current is being asked to find out, and for t greater than 0. So our expression is basically I of t should be equal to I of infinity, using whatever we had used, I0 minus I infinity e raised to minus t by tau. So this is our formula. Now we are going to wait to, so you, to find this, we need to find out I of infinity, we need to find out I of 0. So let's find out I of 0 first. So to find out I of 0, how do you do? We redraw the circuit for t before t is equal to 0, or for 0 minus condition. So which says that time before the switch is closed at time t is equal to 0. This is what is being happening, or the switch is open before that, switch was in the open condition. So we have a circuit which is a 20 volt and 10 volt. You can see that these are in series, positive and negative are in additive polarity. So total voltage will be 30 volt. So I can just write it as a 30 volt. Then there is this 30 ohm, 20 ohm and the half Henry here, right? Now the question is said that having previously steady state is previously attained, which means what? In this condition, the switch is kept on for a long time so that steady state has been reached. So once steady state is reached, what are we going to find out? The current through the inductor. So inductor replaced by short circuit. To find out the steady state, you have to replace this by short circuit. So what would be the current through the inductor? 30 plus 20 is 50 ohm. 30 divided by 50. So current through the inductor is going to be nothing but I0 minus is going to be 30 divided by 50, which is 0.6 ampere, right? So this is the current I0 minus or I0 plus. So we have found out the first thing, I0 we have found out. Now you have to find out I infinity. Now, what is I infinity? The current through the inductor at steady state condition. So steady state is after time t is equal to 0. So it is said that time t is equal to 0, the switch is closed. Now, if the switch is closed, what happens? It is like a short circuit across this elements, which means this much part gets shorted out. Obviously, the current will flow through the will only flow through the short circuit. So effectively, what is going to happen? This part is getting shorted out, and finally we have, so before for t greater than 0, if I draw the circuit, it is going to be the 10 volt source and the 20 ohm resistance, because it's this 10 this one 10 volt, 20 ohm and the half Henry, because this part is getting shorted out, right? So 10 volt, 20 ohm and the half Henry is connected in series, right? So now what would be your I of infinity? Again, replace this inductance by a short circuit. So I have to find out I of infinity. Replace the inductance by a short circuit, right? So if I replace it by short circuit, again, what do I have? This one is short circuited. So 10 by 20, which is a 0.5 ampere. So I infinity is going to be equal to 0.5 ampere. So what have we done here? Understand what we have done. We have found out I infinity, I0. For I0, we drew the circuit before time t is equal to 0. So switch position, whatever the switch position was before time t is equal to 0, we draw the circuit. We find out the current through the inductor by assuming steady state conditions, which means current is equal, the inductor replaced by a short circuit. So the in both the cases we are applying steady state conditions, but this is before time t is equal to 0 and this one is after time t is equal to 0. So I of infinity we have found out. So the total current is going to be equal to I of t is equal to I infinity 0.6 ampere. This one we have already found out. Sorry, I of infinity is 0.5 ampere. This would be 0.5, and I0 minus I infinity. So I0 is 0.6, 0.6 minus 0.5. So 0.6 minus 0.5 e raised to minus T by tau. We'll come to tau. So this is going to be found out as equal to, so 0.6 minus 0.5 is 0.1. So I of t is going to be equal to 0.5 plus e raised to minus t by tau. Let me write it over here. I of t is equal to 0.5 plus e raised to minus t by tau. Now what is your tau here? Tau is nothing but L by R. So this is for the time t greater than 0, whatever circuit is. So there is a resistance of, now resistance of 20 ohm and the inductance is half Henry. So L by R will be 20 divided by half. Now one thing to note is that when you're finding out the tau, that is L by R, you have to replace all the voltage sources or the current sources, or you have to make them equal to 0. So voltage source you replace by short circuit. So whenever you're finding out the equivalent resistance, or when you're finding out time constant, because normally when you're finding out equivalent resistance or whatever, there should not be any voltage source. So when I'm finding out the equivalent resistance in the circuit, or L by R in the circuit, replace this by short circuit. So when I replace this by short circuit, I've got a 20 ohm in series with a half Henry, and L by R tau is equal to, we can find it out as equal to 20, L is half Henry divided by R is equal to 20 ohm, right? Or replacing 0.5 plus e raised to, or minus r by L into t. That is also fine. So e raised to minus of 40 into t. This is our expression. This is the value of I of t for t greater than 0. If some value of t is given, suppose for t is equal to 2 milliseconds, you are asked for t is equal to 2 milliseconds and find out the value. But this is the general expression for I of t. So here we have used the expression of the total response as equal to the steady state value plus the transient response value. So for solving such problems, you need to find out infinity condition, and then you find out the I0 conditions, then use this formula to find out, right? So this is actually a very simple method of solving such problems. Otherwise, you would have to write the whole differential equation and solve this, finding out the constants, etc. So this gives you a very easy way of solving such problems. Again, a very simple example with the inductor, so that we can understand it better. Try to find out the current through the inductor. So the switch is close to position 2 at time t is equal to 0. Before that, it was in position number 1. So finding out, so again, if you write the expression for I of t, it is I of infinity plus I0 minus I infinity e raised to minus t by tau. So substituting this, what is I infinity and what is, let us find out I of 0. For I of 0, draw the circuit. Right? Put this in this position and find out the current through the inductor by assuming that the inductor is a short circuit. So here, everywhere, the assumption is that the circuit has been in this position for a long time, so that steady state has reached. So once steady state has reached, replace the inductor by short circuit. So the total current would be equal to, so I0 would be equal to 50 divided by, so once the inductor is a short circuit, so this replace this by short circuit. So the current is going to be equal to 50 divided by 40, which is 1.25 ampere, right? 5 by 4 ampere. So this is our initial current. Now let us find out the steady state current, or I infinity. So in this condition, it is in position 2. So there is now another source which is 10 volt source, and the 10 volt is connected to 40 ohm and 20 millihenry. So your circuit is going to be now 10 volt in series with the 40 ohm and the 20 millihenry. So what do we have here? I of infinity, again assume that this is a short circuit. Replacing this by a short circuit, we have 10 divided by 40, so 1 by 4, 0.25 ampere. So I infinity is 0.25 ampere. So what is our IT? Total IT is equal to I infinity, that is 0.25, plus I0 minus I infinity. I0 is 1.25. So 1.25 0.25 minus 0.25, which is 1 ampere, plus 1.25 minus 0.25 into e raised to minus t by tau. Remember that the tau which we are using here will be always for the circuit for t greater than 0. So this is for t greater than 0. This circuit tau you have to find out. So tau, again replacing the 10 volt by a short circuit, we have 40 ohm in series with the 20 millihenry. So find out the equivalent tau. So tau is equal to, so this will be equal to 0.25 plus e raised to minus of r by L into t. So for r by r is 40 divided by 20 into 10 raised to minus t. Right? So 40 by 20 is 2. So this is going to be 2000. So 0.25 plus e raised to minus 2000 t. This is the expression. Again, if t, you are asked for a particular time value of time, substitute the value of time and find it. So this is how you solve this problem. So you can see that using this method is very easy and you can easily use it to solve any problem. So now here we have the case with the capacitance, similar case. So now the switch is moved from position 1 to 2 at time t is equal to 0. So similar to what we had done for the inductor, now we are asked to find out the voltage across the capacitance. So we know V of t is equal to V infinity plus V of 0 minus of V of infinity e raised to minus t by tau. Now the in position, so in position 1 there is a voltage source, and position 2 also there is another voltage source. So whatever it is, capacitance, we are going to be assuming that steady state condition is there in both the cases to find out V0 also. So for V0 we put it in position number 1 and the circuit is going to be like this. The circuit is like this. The 100 volt is in series with the 5 kilo ohm resistance and the capacitance 1 microfarad. This is a 100 volt. So what is now, after some time, if you keep this on for a long time, the capacitance reaches steady state and that voltage is nothing but 100 volt. So you can say that your V0 minus is nothing but 100 volt, that is equal to V0 plus. So this is the initial voltage across the capacitance, right? So this one. Now we are going to be finding out V infinity. For that, we want to put the switch in position number 2. So in position number 2, so for t greater than 0, again redrawing the circuit, we have got a 50 volt, sorry, this was minus and this is plus. So this is 50 and 5 kilo ohm and this is the capacitance. Now we can see, since the capacitance is connected, so this is a minus 50, so capacitance will finally reach a minus 50 volt after steady state the voltage. So it's very important that you observe the voltage across how it is connected. The capacitance is connected across minus 50 volts. So finally it will reach up to steady state voltage V infinity is going to be equal to minus 50. So now let's substitute V of t is equal to V of infinity. V of infinity is minus 50. V of 0 is 100 volt. So substituting, I get minus 50 plus V0 minus V infinity. So 100 minus minus 50. So it is 150 plus 150 e raised to minus t by RC. And R is equal to tau is equal to RC is equal to 5000 into how much is the capacitance value, 10 raised to minus 6, or 5 into 10 raised to minus 3. So if I substitute it, I get it as minus 50 plus 150 e raised to minus t divided by RC. So if I substitute, I'll get minus 200 t. So this is the value of the voltage across the capacitance for the total response or the total voltage across the capacitance. See? Because of the initial conditions, that is because the switch was in position number 1 for a long time, the capacitance had initially some voltage across it, right? So that voltage has to be considered. So that voltage is also to be considered in the total voltage which will be there across the capacitance. That is why we write it as V of infinity plus this value into e raised to minus t by tau. Remember, then when we are finding out tau, we have to consider the circuit after time t is equal to 0, that is in position number 2. So this is the case with that of a capacitor. So to summarize, we have understood about the response of source-free and driven RL circuits. So total response can be found as a sum of steady-state response and transient response. Steady-state conditions, how do you obtain? It is replacing the inductor by a short circuit and capacitors by open circuit. This is how we find out steady-state conditions. So for such problems, you find out the initial current or voltage for the inductor or the capacitor. So inductor or the capacitor. So suppose it is a inductor, we find out the current, and suppose it's a capacitor, we find out the voltage. So for the inductor or the capacitor, you find out the initial current or voltage by drawing the circuit at time t is equal to 0 minus and applying steady state condition. So first start with the initial condition, time t is equal to 0 minus, and find out the initial current for the inductor or the initial voltage for the capacitor, but by applying steady state conditions. And by steady state conditions, we mean that you replace the inductor by a short circuit, find out the current, or the capacitor by open circuit, and then find out the voltage across it, right? Now, once you find that, the next step is redraw the circuit for time t greater than 0, and again find out the current or voltage for the inductor and capacitor by drawing the circuit and applying t is equal to infinity for steady state, right? So it is basically at time t is equal to infinity, you again replace the inductor by short circuit or capacitor by open circuit and find out the final current or voltage. Then once we have, the total response can be expressed in this form. So f of t can be either a current or a voltage, and f of infinity plus f0 minus f of infinity e raised to minus t by tau. This would be the expression for our total response. F of infinity is nothing but your steady state response. So this one is steady state or the constant. Remember, even though we are finding out, so do not get confused whenever we are doing steady state. Conditions are done for both in the time t is equal to 0 minus and t is equal to infinity also. But the assumption is that under both the conditions, we have the switch is kept in two positions and assuming steady state conditions. So for t is equal to 0 minus also the switch is kept for a long time so that steady state is reached, right? And also after t greater than 0 also the switch is in another position, and again we are applying steady state conditions. Whatever it is, find the expression will be written as f of infinity plus f0 minus f infinity e raised to minus t by tau. So this part is what we call as a steady state response, and this part is what we call as the transient response, transient part. Not the whole f0 minus f infinity e raised to minus t by tau. Since it's an exponentially decaying part, you can see that it will decay down to 0 after some time, and finally you will be left with only the steady state. So this is about transient analysis in RL and RC circuits with source or without source. So with source is called as driven circuit, and without source are called as source-free circuits. Okay. Thank you.